I'm going to house is too. Alright. I gotta finish rewriting my very, very shitty speech. Oh yeah, that thing. Trademark. Joining us that one part. You know what I'm talking about. Alright.
Raw, can you leave?
Yes. Oh shit. Yeah.
Hi.
So I like this is just the post one.
How could there be no mic?
Yeah.
Hey guys. Hey. Welcome back to Deep Learning Decal. Welcome back to day 3. So, without further ado, let's get started. I hope you've all finalized your project or reading group decision. I think today we'll give you some time to talk to other people and maybe find a group for your project. Start to get some ideas flowing. Maybe we'll give you in the middle of class, which is a break, and we'll give you some time to talk to other people. No deliverables yet. We'll be doing reading group stuff. So I think everyone should be clear with the reading group. There's instructions on Piazza, so questions should be due by a certain date. The paper submitted should be due by a certain date. So that's all on Piazza. Michael is going to talk about RNNs today. Michael's awesome. And after his lecture, we're going to have a reading group by Benjamin Kim. Is he here? Mr. Ben Kim. Ben Kim. Who's doing reading group today? Do you know who's doing reading group today?
No.
Can you check on Piazza, please?
Not on the Piazza.
Okay, I will do everything. Are there any questions about anything in the meantime? Sweet. So, yeah, reading group today is Benjamin Kim. He's not here. Benjamin Kim. Okay, hopefully he shows up soon. If there's no questions, we'll get started with the topic for today, which is recurrent neural networks. A very powerful class of networks that, as you'll learn, are sequence of sequence models. They can take in a sequence of inputs and output a sequence of inputs, and anything in between. And they've been very popularized recently. And I think they were invented in the mid-1980s. Michael Jordan was one of the co-inventors of them. And now they've been heavily used to a lot of different things, but Mike will tell you all about it.
Alright, let's get started. So, I'm going to be talking about recurrent neural nets. Let's just jump right in. So, basically what we'll cover is some background on why we need recurrent neural nets. We'll talk about the most basic vanilla implementation of a neural net. Then we'll talk about the LSTM, which is the most commonly used neural net that has recurrence in it. It's used in a lot of applications these days and in state-of-the-art research. Finally, we'll have time for questions, but you can also ask me questions at any time. Feel free to interrupt. Alright. So, where are we? So far we've talked about fully connected neural nets and convolutional neural nets. In both of these cases, we learn a fixed mapping from the input to the output. You learn your weights, and then each layer is just a fixed function that takes the input, applies some function, then applies another function, and so on until you get an output. There's no concept of memory, and in a lot of problems, we need some sort of memory to better understand and solve the problem. So, just as an example, recurrent neural nets, the architecture is much more flexible. So rather than having just one single input and one single output, you can have one input and many inputs and one output, and many inputs and many outputs. So an example of this would be if you have an image and you want to output a description of what the image states, like a caption of what the image, an image captioning problem, it would be a one-to-many problem. An example of a many-to-one problem would be, suppose you observe a video and there's some object in the video. Your goal is to detect what the object in the video is. Then that's an example of a video having multiple inputs. Each frame of the video is a different input. And then finally you have an output, which is your classification of what's in the video. Many-to-many is like one of the most common models. It's used in translation. So if you have a source sentence from one language, you might want to translate it to another sentence. So Google Translate has a recurrent neural network behind the scenes as well. So there are many different applications, and we'll see some as we progress as well. Yeah.
So with the many-to-many use of a recurrent neural network, would you typically in practice wait until you have observed your entire input sequence before you generate an output sequence?
Yeah, that's a good question. So it really does depend on your application. We'll see one example where you can just, and actually it's called a character level RNN. So what you're doing is you're trying to generate a sentence one character at a time. So in that case, it kind of makes more sense to observe one thing than just predict the next character immediately afterwards. Whereas in some cases, you want the entire context of all your inputs before you predict the outputs. So it really depends on your problem. All right, any other questions? Cool. Let's jump right in. So, yeah, I guess I just described many of the things here. So, Andre Karpathy, he wrote a really nice blog post about many of the things recurrent neural nets can do. You can look this post up. Karpathy, if you don't know him, he's like a very famous guy these days. He taught a really good class at Stanford, and he's now director of AI research at Tesla. So basically, he talks about how recurrent neural nets can do all types of things, including speech recognition, language modeling, translation, and image capture. Yeah, and this is something I'll also mention more later. So we'll first discuss the more basic vanilla version of the recurrent neural net. It's something that works, but not extremely well. We'll see why it doesn't work as well as we would like it to, and then we'll talk about an alternative called the LSTM, and maybe the GRU as well. Okay, so this is the basic structure of a recurrent neural net. Basically what goes on here is you have an input at every state potentially, and you might have an output potentially at every state. But the key is the thing in the middle. It's the hidden state. And what the hidden state does is it's the internal memory of the recurrent neural net. So it tries to keep track of what's going on. It remembers information relevant to your particular task. So there are kind of two ways you can go about like picturing what a recurrent neural net does. One way is to just look at this thing that has this self loop. I think the one that makes more sense intuitively at first is you can picture a neural net that progresses through time. So I mean time in the sense of as you move further in time, you get more and more inputs. So initially you get an input at times t equals 0, then you get another input here and another input here and so on. So what happens is when you get the input, you also have what the hidden state is at the previous time step, so what's here. And what you want to do is you want to do some sort of operation to update the hidden state based on your new information. So for example, if you're trying to translate between two sentences, you might have observed an adjective previously, and now you have a noun. So you want to update the information to tell you, oh, I have an adjective and a noun. I need to output the corresponding description in another language. So I'll go into the equation and then we can answer more questions. So basically, this is the update equation for the hidden state. This is like the most important conceptual idea. It's the memory of the network. And what you have here is you have the input at time step t, and you also have the previous hidden state. So U and W are just weight matrices that figure out like what's the best information we want to capture at this given time step. You multiply and add them together, and then f is an activation function to ensure nonlinearity. So we typically use something like can_h or value, and this is the update to the hidden state. So remember I said earlier, you don't necessarily need an output every time step, but if you do have an output, it's pretty common to do something like softmax. Another weight matrix we'll call it V times the hidden state. So this V matrix determines what relevant information we want from the hidden state, and it maps it into the output. So the reason we might want to do something like a softmax, so softmax takes in a bunch of numbers and then converts it to a probability distribution by raising it to e to the power of whatever the values are and normalizing. So the reason we might want to do something like this is if we're doing like a character language model, we have a bunch of characters we might want to predict, and we want a probability distribution over what the most probable next character is. Okay. So are there any questions on this? This is like the most important part, probably. Yeah.
Can you go back to the slide? So
This
so
one?
the O.
Yeah.
The T.
Yeah.
Like you said, not everything has to have the output.
Yeah.
You explain that.
What I mean is, so if you go back to this slide here, you don't need an output for every single time step because you might only want one single output. So like your task might be, my example earlier was video classification. So you're given a video and your goal is to try to predict what the object is within the video, or like, yeah, so what the object is within the video. So you observe a whole sequence of frames, and perhaps the object is actually moving and only one of the frames actually has the object, but you need a recurrent neural net to like process all the information, but you only have one final output, and that's the output that's your goal, essentially.
I see. So then, you know that you apply the activation function, but that isn't necessarily the output.
Yeah, so, well, if you don't have an output here, you don't need to compute the activation function, right? Because, as in like the neural nets we've done in the past, you only care about what your final goal is, and you define your loss function based on what you want your final goal to be. So if our final goal is to maximize our classification accuracy on this video classification task, then our loss function would be just based on this thing. You could have an output here, but not included in the loss. All that matters is like you have the correct loss for your task. Okay. Any other questions? Okay. So yeah, this is what so one important thing to mention here is that we can imagine unfolding the network into something like this. So, for example, if we're modeling a sentence that has up to 10 words, this would be length 10 long. But kind of the key here, and the reason this works well, is because all of the U, W, and V matrices, they're all shared between every single layer. So you're going to update them simultaneously, and like when you do backpropagation. The reason they're all shared is they all do the same goal. Every time you have a new input, the U matrix tells you what information from the input you want to add to your hidden state. The W matrix tells you what of the previous hidden state you want to remember for your next hidden state. And the V matrix maps from your hidden state to the output. So since they accomplish the same goals at every single time step, the U, W, and V matrices are the same. So this is kind of similar to the parameter sharing in the convolutional neural net section. We have fewer parameters because they're all shared since they accomplish the same function. Okay, so yeah, so this reduces the number we need to let. And as I said before, you don't necessarily need inputs and outputs at every time step. The key feature that the recurrent neural net has is the hidden state. So all the networks we've done before and all the convolutional fancy architectures, they don't have a hidden state, which means they don't have any memory or a concept of what the previous inputs were. This is able to remember what the previous inputs were. Okay, any questions? Alright. So in terms of optimizing the recurrent neural net, the initialization is pretty much the same thing as before. You typically initialize your hidden state to be a vector of all zeros because you have no knowledge before you see any of the inputs. And then you define a loss function and use backpropagation to update the weights. So because we're using like linear multiplications and tanh functions, the gradient computations are pretty similar to the ones we've seen before, and you can update the weights accordingly. But one problem with recurrent neural nets, though, is the vanishing gradient problem. So the idea is that if we have this update rule and you apply it over and over again, tanh is going to output a value between -1 and 1. So the magnitude of tanh is less than 1. So as you apply the function over and over again, essentially the value of the hidden state is going to get squashed. So it's really hard to learn long-term dependencies, which is what you actually want in many of these problems. So in order to get an accurate model of sentence structure or language model, you want to remember stuff across different sentences. But if you have a vanishing gradient problem, which means that the gradient from one time step isn't dependent on stuff 10 time steps into the future, that means you're not able to capture the long-term dependencies that we really actually do want to capture. So that's kind of the key issue behind just this vanilla recurrent neural net.
So that's why you would choose arctan tanh or reboot compared to sleep.
Yeah, so ReLU actually helps address this problem a little bit because it's either 0 or 1.
But that's also problematic too, which is why they use linear reboot.
Yeah.
Slightly negative slope.
Yeah. But we'll see, in practice, you generally use LSTM, which we'll describe as well. Yeah. So if you want to understand this problem at a deeper level, you can try doing backpropagation and seeing why it depends on the activation function and depends on the maximum eigenvalue. So if the maximum eigenvalue of these matrices is really big, then our gradient can actually potentially explode, but that's less of a problem because when your gradient explodes, during training time you generally observe not a number errors, whereas the other problem of a vanishing gradient, that's more sinister because it's like a silent bug. You don't realize it's a problem until you actually look at your outputs and you see that, oh, we aren't able to capture long-term dependencies that well. Okay. Yeah, so as I said, using LSTMs or GRU is one way to solve this problem.
So if you had, are there situations with an RNN you want to have a very short memory, so you would still not use an LSTM or GRU? If the vanishing gradient problem is not as big an issue?
Yeah, it could be not as big an issue, but what we'll see is that LSTM, it actually has just strictly more functionality in some sense. You can force it to forget stuff. It's manually an option to forget stuff, or you can remember information from a really long time horizon. Yeah.
I just had a clarification about the tanh.
Yeah.
You say the tanh function, that actually contributes to the vanishing gradient.
Yeah.
Why is it
So tanh is going to output a value between -1 and 1. So if you think about applying many tanh, that's going to just shrink whatever your actual value is. So that's the high level and slightly hand-wavy intuition. Okay. Yeah, good. Any other questions? Yeah.
Is there a major downside to using the RNN? Because it seems like it is more flexible.
It's kind of good to conceptually understand what's going on, the idea of having a hidden state, but I think in practice you almost always use LSTM. Yeah. Yeah.
This is a terrible question, but do you prefer RNNs or CNNs?
Well, sometimes you actually use some combination of both, so that's not really a...
Yeah, I said it.
I think I personally enjoy CNNs more, but Oh wow, did I hurt your feelings? Okay, but that's like a moot point. It doesn't really. You use both. They're both like very applicable for many of the different problems. Okay, cool. Any other questions? Okay. Alright, so we'll talk about the LSTM. The GRU is like a slightly simpler version of the LSTM, but the LSTM is like the go-to thing most people use. So this is one way to address the vanishing gradient problem, and the reason we want to address the vanishing gradient problem is because we want to remember long-term dependencies. So one example of this is the neural net. So you might be trying to translate a sentence that's really long or a paragraph, and it might begin with something like, I grew up in France, and then a little bit later it says, I speak fluent blank, and your goal is to try to predict what the next word is. So in this case, you want to remember that the word France came up earlier because the context of France is important later on. This is just like one particular example of why you need to handle long-term dependencies. So the LSTM is this fancy-looking thing that is able to better handle these dependencies. Okay, so like this is what pictorially the LSTM looks like. We'll like dive into like each of the specific components. The concept here is that rather than having just one single hidden state, there's a cell state and a hidden state. They're both technically like hidden states that remember different information, but you can think of the cell state as like a highway that goes directly through the LSTM. So if you wanted to remember information for a really long time, you can do so, because the cell state just like flows through time through different inputs, but you can modify it as you like. Whereas the hidden state is like something that's more short term and is able to modify, retrieve, and alter the long term memory. So the hidden state is the one down here. It deals with like shorter term things. So the cell state is up here and deals with more long term dependencies. But we'll see why. Okay, so we have the cell state up here. It's gonna be updated with this operation. This is an element-wise multiplication of ft and it. I'll explain what ft and it are. So the ft is called the forget gate, and it is called the input gate. The idea is that the cell state, you can optionally remember stuff from the previous cell state, or you can add more stuff using input gates. All right. So how is ft determined? So as before, you would have input the previous hidden state and input the new input at this time step, so this might be a word. So what you do is the forget gate is equal to sigmoid applied to this whole thing here. So I guess the key thing to notice is that sigmoid is going to always output a number between 0 and 1. So what the forget gate is doing is it's looking at the previous hidden state and the new input, and it's deciding. So for example, if you observe the word English, whereas you've seen the word French in the past, you might decide, oh, I might be able to forget the word French. So that's just like a silly example. But the neural network is able to like optionally forget stuff in the cell state using this operation. So we saw before we have some operation that updates the cell state. In order to compute the actual update to the cell state, we have this input gate here. This decides, like, using the short-term memory, what long-term information do we want to store into the cell state. So the way we compute that is via sigmoid. So this is like the exact same operation you see here, except we have a different weight matrix. So we use WF here, and we use a WI here. I should mention in this notation, you'll notice HT minus 1 comma XT. All that means is that we're concatenating the previous hidden state and the current new input and putting it in one giant vector and multiplying by the weight matrix. So this is like a measure of what we need to record into the cell state going forward. In addition to deciding what we need to record, the neural network also computes something called, we'll call it C tilde of t. So this is deciding like how much you should record. This is deciding what is the actual information you record. So again, it's like the same thing inside here with a different weight matrix. And again, what this does is it decides what new information you want to record. So what you'll notice in all of these things is that the LSTM is very modular in the sense that information it gets to be very flexible in terms of like what information it's forgetting, what new information is added, because it's breaking down each of these components into like specific operations. Cool. Any questions on these two steps here? Yeah.
So, can you just go over more exactly the example? C is the cell, I is the input,
Yeah. I is input, F is forget, C is the self state, H is a hidden state, and X is like the input at time t. XT is the input. Yeah. Yeah. Cool. And then finally, this is the update equation we had before. Once you computed the quantities f of t, I of t, and c tilde sub t, you update your cell state. So you forget information from the previous cell state if you want to. Since f of t here is a sigmoid, it can be up to the value 1. So basically, if you don't want to forget anything, you can choose not to forget anything. And then you can also decide what you want to add in the form of this it times c tilde of t. All right. So that's how you add new information into your cell state. This is like storing stuff into long-term memory. Notice here that we don't have any like nonlinear operation. So whereas in the RNN we have like a tanh or a belly here, there's no non-linearity here. So whatever's in the cell state can just flow into future cell states. It's just straight up, not unmodified. Yeah, question? I is a, it's called the input gate. So I determines what new information we want to add into the cell state. C tilde determines like what information you want to add. I of t determines like how much of that information you're adding. So if you look at the equations back here, I of t is like going to be a value. I of t is a value between 0 and 1 because we have a sigmoid here. It's like saying, if we want to be more concrete, let's say we're doing a task where let's just do translation. So if we're trying to translate between two different languages and we observe a verb, then what I of t might do is it tries to store that verb into the cell state. I guess you don't have to worry too much about the exact interpretations of these. We'll see more of like why exactly the cell state works a little bit later on. Because I'm not sure anyone really understands why these work, like precisely the way they do, because what you'll notice is that all these operations seem like very precise for having like this fancy looking function. What we'll observe later on is that people have done research on this topic, and essentially what happens is if you change these things slightly, so for example, if you allow C tilde of t to t into the previous cell state, so you pass in the previous cell state here as well, the architecture performs like very close to the architecture here. So like small tweaks to the architecture have very little impact on the actual final performance. The basic idea of having two hidden states is still important though. So I'll link a paper later on that talks about that. Okay. Any other questions? Alright. So we're almost done here. In order to get the output, what we're doing is one more sigmoid operation. onto. So this output, what it does is it tries to capture how much of the cell state we want to extract and put into the output. So it's another sigmoid looking operation based on your weight of the output matrix and your input and previous hidden state. Finally, we also update the hidden state, which is the short-term memory, with the output times the tanh of the cell state. Okay, yeah.
So output determines how much of the information from the cell state is going to be, or from the hidden state is propagated to the next hidden state. OT, is that the
The output, so this could be directly the output of the neural net, or you might have one more fully connected net after the output layer. But this also determines how much of the cell state flows into the hidden state. Yeah.
Oh, okay.
Mm-hmm. Okay. And so this next page here, it's pretty cool. You don't have to worry exactly about what the colors are. So this is recording the cell state and what specific things in the cell state do. So if we look at one particular cell in the cell state, what you see after you train the LSTM is that as you input text, the activation of that particular cell is going to. So this is color-coded such that 0 is the lowest, 1 is the highest, or something like that. So if you approach the end of a line, it decides, oh, we need to output a new line character very soon. So there's a particular cell that's responsible for determining how close to the end of a line we are. And using that cell, we can decide whether or not we should predict a new line. Similarly, there's also a cell state that captures whether or not you're within a quote. So here you'll notice that when there's a quotation mark, the cell state lights up. So input gate and some combination of the C tilde of P decides we need to record this information, and then it's stored. So later on, when the quote ends, it's this cell state realizes, okay, we've reached the end of a quote, and we don't need to output another quotation again. So this is really cool. There's memory. It actually learns something useful and interpretable. Similarly, if you want to model code, so someone's trained an LSTM to model code and to generate code, there's a specific cell state that remembers if conditions. So if you're inside an if condition, you have some left bracket that remembers that, oh, we need a left parentheses afterwards. And it lights up whenever you see the open bracket for if condition. But then, Andre Karthi wrote a paper on different things you can interpret about cell states. A lot of the cell states aren't quite as easily interpretable, so there's ones that light up quite randomly and we don't have a clear interpretation. But the nice thing is that just by training it with the loss function, we do get nice behavior and observe stuff like this. So this is a neat view of why stuff actually works. Questions on this slide? Okay, so as I mentioned before, if we look back at this architecture, I guess this is highlighting specific parts of the architecture, but if you look back at this architecture here, you can do many different variants. So rather than having a forget gate and an input gate, you can just define the input gate to be 1 minus a forget gate, and stuff like that. And basically there's a paper, it's called LSTM, a search space odyssey. It was written in 2015, and it talks about trying many of these different variations as long together with a huge random hyperparameter sweep. It does 5,400 total experiments on 3 different common benchmark tasks, and their final conclusion is that they all work about the same. So there's no statistically significant difference to using a particular variant over other ones. So if you're implementing this in TensorFlow or Keras or something like that, you can just stick with the standard implementation, and you'll get pretty much very solid performance. All right, so we'll do a quick demo. So we'll do a character RNN, because these are pretty fun, and you can use them to generate text. So what happens here is you input a bunch of text, and the goal of the RNN is to predict the next character in the text. So if you input an H, it does something to the hidden layer, and then the output layer is like a softmax applied to a weight matrix times a hidden layer, and you get a bunch of different values. You sample from those values to draw out your next letter, and then you feed your next letter back in here as the next input. So this is called a character RNN. I ran this a bit earlier, and you can look at the outputs. So basically, so I trained this on a bunch of Obama speeches, and at the very beginning of training, you get complete gibberish. So I'll explain the temperatures here. What the temperature does is it's like the temperature is something you apply to your softmax. So what softmax does is you have like a bunch of different values, x1, x2, all the way to xn. What the temperature does is it's going to do e to the x sub I divided by the temperature over summation e to the x sub I temperature across all I. So this is a probability of action, probability of character I guess. So it's like a scaling term on the x of I terms. Basically what it does is if you decrease the temperature, you're going to be more likely to choose the most likely sequences. Because how reduced temperature means that the values are going to be more spread apart. So a value that's bigger is just going to dominate the entire normalized softmax probability. And higher temperatures are going to give you more random and potentially more creative sequences. So let's scroll down a little. So after iteration 1, it just learns like the most common patterns, the state of the world, who are still because of the world, who are still strong, and see a country. So it's learning some relevant stuff after just like one loop through an entire data set, and then we can keep going. So for some reason, the temperature 0.3 here, it says the right of the states of the United States of America, then it outputs a bunch of new line characters for some reason. And then it does like, good afternoon, everybody, God bless you, and so on. So, interesting things. We can move forward, and you can see as you do more iterations, the stuff actually kind of makes sense. So it depends on like how long your input sequences are. One thing I forgot to mention is you don't feed like your entire giant 500,000 word thing directly into your RNN. You chop it up into slices, and you input like 80 characters at a time. Otherwise, it takes forever to train, and you can't backprop through the whole thing practically anyways. But then stuff makes more and more sense as you increase the number of training iterations. So I didn't play too much with the architecture, but one thing you can see is that after training and trying to generate a few longer sequences, you can see that the sequences kind of do make sense, but not long-term sense, because it's not, I don't think there's enough data in the Obama data set to capture like useful long-term dependencies that are already in the data set, so it'll just say things like from different speeches. So you can read some of them here. I guess I'll read one out loud. So if we look at this one, it says the fact that they have the right to determine their own destiny, period, in the middle of the country will continue to confront the concerns of American life and liberty and the promise of a new country to afford the cost of healthcare to the middle class. And that's why we must do something about it. Yeah.
I noticed that at the beginning it always begins with the. Is there like a reason for that? Is that like something you trained it?
Oh, that's a good question. So essentially what I did was I seeded it. So you can seed your input with like any arbitrary string you want. What I did in this case was I seeded it with the empty string. So that means the most likely next character after an empty space is T. And then from T, it automatically decides to generate H and E after that. So I guess that's why, yeah. So the does show up a lot in his speeches, so that's why if you put a blank space, you get the. Well, you can play around and like seed it with some weird random word and see what happens as well. Cool. Any other? Yeah.
So there's no like semantic comprehension going on? Or do you have
well-
a comment on that?
What do you mean by semantic comprehension?
Like there's no symbolic understanding or like comprehension of what meaning is?
No, I don't think so. I would think of it as it does like a good job of remembering some recent stuff it says,
Yeah.
and then it tries to predict relevant next. Because this is working at a character level, so
Yeah.
it's pretty crazy that you can have like 10 words actually kind of make sense. If you do like a word level thing, it'll make even more sense because words, you'll learn to associate meanings of words with each other. But I don't think we have like a nice way of interpreting like semantics from this yet. Yeah. Any other questions? Okay. So, yeah, if we go back here, so Berkeley also has a bunch of different examples. He fed in a bunch of LaTeX, and you can also actually generate like realistic-looking math papers with lemmas and corollaries and nice-looking proofs, but gibberish proofs, using the same method. So, yeah, if you have time, you can feel free to grab an implementation online, feed in your own data source, train it, and see what happens. Like, you can plug in poems, you can plug in Shakespeare, you can plug in, like, literally anything that has enough data, and you'll get something with some semblance of meaning out of it. So that's really cool. Yeah, so are there any questions before we move into this section? Yeah.
Do you know about the Google Translate implementation of RNN?
I know Google Translate does have a paper like, describing how their method works, so I haven't read it thoroughly, but it's something about having a really powerful like LSTM between any pair of languages. So I think they train specific LSTMs for each pair of languages because there's like different things you need to remember for different combinations of languages.
Do you mean like from English to French, English to Japanese?
Yeah, there's different models for it.
I thought that's what it was replacing that. That it has LSTMs for each language to machine language that is then retranslated to your target language.
Not that I'm aware of. We might be, right. Yeah, you have something to add?
Well, actually, I have something to add to what you said.
Yeah.
I actually read about that recently, and from what I read, it sounded like they were translating any language into English first, and then translating it from English to another language. So then it can simplify how many models they had to train, but it still requires multiple models that you train to go between any language.
Well, it just requires one for each language.
Yeah.
But multiple common.
I guess that probably makes sense. Yeah. Yeah. I don't know. You have to look it up for it. We can talk about it later.
Another question.
Yeah.
I'll just ask you this at the end, actually.
Okay.
Cool. So what I like to do right now is a couple things. First thing is I want to give you some time to fill out the attendance sheet for today. So here's the URL, tinyurl.com/rnns-day3. And just to remind you all the slides that will be posted on our GitHub repo. So if you're looking for the slides from today, they're posted on the Deep Learning Decal GitHub. Lastly, we'll take a little short break before we get into the reading group. And during that break, I really want to give you guys some time to talk to each other and find a potential group for your project. I know the proposal isn't due for 2 or 3 more weeks, but once it gets going, it really gets going quickly. So I recommend you find a group early and find a topic early and don't procrastinate. So we'll give you like 10 minutes or so to talk to some people, maybe think of an idea. You can talk to us as well. By the way, you have to stay for reading group if you're going to fill out the attendance form. You can't just fill out the attendance form and leave. We'll take away your attendance points. That's just not fair. Cool, yeah, so let's take a break and do both those things. What? Cool. Ben, Kim?
Yeah, I
Cool.
was pretty sick with the last few days.
Oh, no, it looks good. Michael, can we use your computer to present just because you're recording? And if we unplug it, it shouldn't take more than half an hour, 45 minutes. So, I'm going to blank the screen, and I emailed you his presentation. Do you think you can open it from your emails? Is it cool if you use this computer?
Yeah, it's just a Google slide.
Yeah, we have it. Do you have the questions already?
Yeah.
Should be that one.
It was basically very hard.
Yeah. Nice.
It says that I just.
Oh, for the attendance form? Which
Yeah, I might be on the lights.
Oh yeah, you need to do it on your Berkeley email, I think, about the attendance sheet. So this is the time to find a project group if you don't already have one. Now is the time. Do so.
Present an image.
CNNs.
I'm interested in
Yeah. You're in reading group? Let's just do it anyway. I'm in project group, I'm presenting today. Yeah. Audio, CNNs are
Yeah. Probably can do the learning of your
Yeah, I know that.
Project partners, who needs one?
I do.
Up to 3 in your class.
I just wrote down. So yeah, there's only probably two. I think maybe that's the reason people said like it's like implementation and mathematics. You see the Facebook builds? Oh, that was anyone saying there's something called terrible. But like it's only gonna get faster.
Well, I think for the top one, you get more advanced. Region,